Hi all, welcome to my channel. This is E. Manjula, lecturer in Electrical and Electronic Engineering, Government Institute of Electronics. So today in this session we will discuss about the representation of the current voltage with their vector diagrams and derivation, which is the relationship between the voltage and current in pure resistor and also inductor and capacitor. And on completion of this period, you could able to know that identification of difference between the resistive, inductive, and capacitive circuits, understanding the concepts of capacitive reactive, and we will even derive the relationship for current in capacitive circuits and also inductive circuits. And you will also understand the inductive reactance and the difference between the resistive and inductive circuits. So do we know that the differences between the scalar and vector? So what is a vector diagram? How to represent a graphical method and a vector diagram. So today we will see it. We'll first go for the definition of a vector. So what is a vector? A vector is a physical quantity which has both the magnitude and the direction. And the graphical representation of the current and voltage method. And here it is showing the graphical representation of the current here in this x-axis. It is theta or omega t and time. Okay. And in the y-axis, it is a current or it may be the voltage also. So if you observe, it is a sine wave. First, it is increasing and decreasing. This is a positive half, and decreasing and increasing, it is a negative half. Okay, this is a phasor representation. So what are the advantages of the vector representation? So we know that a phasor, how it is represented, either the voltage or else the current. Then why we have to go for the vector, and what is an advantage of the vector representation? We will check it. Okay. So here vector method referred over a graphical method because vector methods greatly simplifies the problems in AC circuits. So by using the vector methods, it is very easy to solve a very difficult problems in an AC circuits. So here the vector diagram of voltage and a current circuit. So here if you observe, this is a current and here this is a voltage. Okay. The relationship between the voltage and current in a pure resistive circuit. So this is a circuit, here an AC power source, resistance and current. Yes, we can observe that the current is passing from the source to a resistive, through the resistive and again back to the source. And from this waveform, we can also say that both the voltage and current both are in phase. See, if we observe, they both are in phase. The diagram of a pure resistive circuit we have seen. So let we found the relationship between the voltage and the current. So let the applied voltage is given by the equation. The instantaneous value V is equals to V maximum sine theta, which is equals to V maximum sine omega t. Now we are taking this is an equation 1. And let R is a ohmic resistance and I is an instantaneous current. So ohmic drop will be, that is V is equals to I into R, and we are taking this as an equation 2. So keeping the values of V in equation 1, we get that V is equals to V maximum sine omega t, which is equals to I into R. So here, this is small I, okay, that is instantaneous current. So I is equals to V maximum sine omega t by R is here we are taking it this equation as 3. So when sine omega t is equals to 1, then I is equals to V maximum by R. So here, when we are treating this, taking this as 1, then I will be equal to V maximum by R. Okay. So here, I is maximum current when sine omega t is equals to 1. So, maximum current I maximum is equals to V maximum by R. So, substituting the value of I maximum in equation 3, we get I is equals to I maximum sine omega t. Thus, in the pure resistive circuit, V is equals to V maximum sine omega and I is equals to I maximum sine omega t. Okay. So we can directly tell that by these two equations, by observing these two equations, V and I will be always phase in a pure resistive circuit. Okay. So this is actually a vector diagram representation. Okay. So the vector diagram of voltage and current. So here this is the current and this is the voltage, which is a graphical representation. Now the same taking the magnitude, so higher the voltage is having a higher magnitude, so this is the voltage V and I is also in phase with the voltage, so I will be falling on V, okay, with some lesser magnitude as observed here. Okay, so this is a vector diagram of a resistive circuit. So what will be the power in a pure resistive circuit? Instantaneous power P is equals to V and I. V and I both are instantaneous value, which is equals to V maximum, I maximum sine 2 omega t. So I maximum, V maximum into 1 minus cos of 2 omega t, V maximum, I maximum divided by 2 minus V maximum, I maximum sine omega t into by 2. Okay. So this is sine square omega 2. So here the first part V maximum I maximum by 2 is a constant and the second part V maximum I maximum cos 2 omega t by 2 is a fluctuating part. So here V is equals to V into I, which is equals to V maximum I maximum sine square omega t. Okay. So so here when we do V maximum I maximum into 1 minus cos 2 omega t, which is equals to V maximum I maximum by 2 minus V maximum I maximum cos 2 omega 2 by 2. So here the first part is constant and the second part V maximum I maximum cos 2 omega t by 2 is fluctuating part and depends on the frequency of the voltage or current wave. For a complete cycle, cos 2 omega t is 0. Therefore, power for the whole cycle P is equals to V maximum I maximum by 2. That is V maximum by root 2, I maximum by root 2. So that is P is equals to V and I watts, where V and I are the RMS values. So we have already discussed about the RMS. The RMS value is V maximum by root 2. Okay. So we are taking this directly as an RMS value. So the instantaneous value of the power is equals to the V into I are the RMS values of the voltage and current respectively. So in a pure resistive circuit, the power in whole cycle is never zero. Okay. So we will go to one problem so that we could able to understand this resistive circuit better. So an AC circuit consisting of a pure resistance of 30 ohms and is connected across an AC supply of 220 volts 50 hertz. Find the current, power consumed and sinusoidal equation for voltage and current. So R is equals to 30 ohms, V is equals to 220 volts, F is equals to 50 hertz. This is a given data, and current I is equals to V by R, which is equals to 220 by 30, which is equals to 7.3 amps. So the power consumed P is equals to V into I, which is equals to 7.3 into 220, which is giving 1606 watts, and VRMS, which is equals to 220 watts. And what will be the V maximum? V maximum is equals to under root 2 into V, which is equals to root 2 into 220, which is equals to 3.11. So 311.08 volts. Similarly, I maximum, which is equals to under root 2 into I. So here I is 7.3. So 7.3, that is an RMS value. So root 2 into the RMS value will give you the maximum value. So that is 10.32 amperes. Okay. So omega is equals to 2 into pi into f, which is equals to 2 into pi into 50, which is equals to 314 radians per second. So here in the given equation, that what we have to find out, we have to find out the current, power consumed and the sinusoidal equations of the voltage and currents. So till now we have found that the current and the power, the current and the voltage. Okay. So now we will see the equations of the voltage and also the current. Equation of the voltage, instantaneous value V is equals to V maximum sin omega t. So which is equals to V maximum is 311.08 sin 314 into t volts. Okay. Likewise, same the current equation, which is equals to I is equals to I maximum sin omega t, where I is equals to I maximum value is 10.32. Directly we can substitute, and sin of omega value is 314 into t amps. So here in this power also given. Okay, so the power need to be calculated. Okay, so power is already calculated. Okay, fine. So by this you could able to understand how to calculate in a pure resistive circuits. Okay. So now we will go for the inductance. What is an inductance and what is the nature of the instantaneous power in an inductive circuit? And instantaneous power in a pure circuits is always positive. Remember this, okay? So instantaneous AC power in a pure resistive circuit is always positive. So this is an E voltage and this is a current, okay? So both are positive, positive, both are negative, positive. Okay, so this is the power. So always the power is positive in a resistive circuits. So what is an inductor? Inductor usually a coil of wire. Inductor opposes the change in current through them by dropping a voltage directly proportional to the rate of change of current. So, if current is increasing in magnitude, the induced voltage will push against the electrons flow. If current is decreased, the polarity will reverse and push with the electrons flow to oppose the decrease. So here this is a inductor L and AC source, voltage source is connected to an inductor. You can see this is an IL current which is passing and this is a current which is coming out. Both are same as it is series. Okay. So here EL and IL, this is a vector diagram. So the voltage and the current, if as it is a pure inductor, the current which always lags by the voltage by 90 degrees. Okay. So here we will see the relationship between the current and voltage in pure inductive circuits. The relationship between the voltage dropped across the inductor and rate of current change through the inductor in a such a way that E is equals to L into di by dt. Okay. So V instantaneous value V is equals to V maximum sin omega t. E is equals to minus L into di by dt. So we know that V is equals to E according to this equation. Okay. So V is equals to minus E, which is equals to L into di by dt. Okay. So V maximum sin omega t is equals to L into di by dt. So di di is equals to V maximum by L into sin of omega t. So in order to get I, we have to integrate the equation so that we can get I value. So integration of di is equals to integration of V maximum L into sin omega t dt. So I is equals to V maximum by L constant we kept outside the integration. So integration of omega sin omega t dt, which will give V maximum by L minus cos omega t by omega. Okay. So V maximum L, which this part is sin omega t minus pi by 2. So here I maximum value is equals to, here omega will be there. Okay, omega. So this is minus cos omega t. So the minus cos omega t, I can write it as sin omega t minus pi by 2. Okay. So omega will come out. So V maximum sin omega t. So V maximum sin omega, V maximum by omega L is the I maximum value. Okay. So I into I maximum sin omega t minus pi by 2. So here graphical representation of the voltage and current in pure inductor. So this is a current, the red one is current and blue one is the voltage. So when voltage started, according to the equation, we can say that the current is starting after 90 degrees the voltage. Okay. So this is the V and this is a current representations. Current slope and voltage slope, current slope maximum negative and voltage slope maximum negative. Okay. So now the inductive reactance XL. It is the ratio of the magnitudes of the voltage and the current. It is measured in ohms. So V maximum is equals to XL by IM. So XL is given by 2 pi FL, that is omega L. So we define the self-inductance of a coil thus pi bt is equals to L into I of t. So the voltage that appears across an inductor is due to its own magnetic field and Faraday's law of the electromagnetic induction and Faraday's laws of electromagnetic induction. So the current I of t in a coil sets up a magnetic field whose magnetic flux is pi b and is proportional to the field strength which is proportional to the current flowing in the inductor. So here instantaneous power P is equals to V into I. So V is nothing but V maximum sin omega t, V into I. So here V is equals to V maximum sin omega t and I is equals to I maximum sin omega t minus pi by 2. So V maximum I maximum sin omega t minus cos omega t. So here V minus V maximum I maximum by 2 into 2 of sin omega t cos omega t which is equals to sin of 2 omega t which is equals to P is equals to minus V maximum I maximum by 2 sin 2 omega t. So average power consumed by the circuit over a complete circuit is P is equals to 1 by 2 pi 0 to 2 pi minus V maximum I maximum by 2 into 2 into sine omega t d of omega t which is equals to 0. So this is a power you observe, okay, positive negative positive negative, okay. So it means that the inductor is relieving power back to the circuit while a positive power means that it is absorbing power from the circuit, okay. Positive power means that it is absorbing the power from the circuit. So we will go through one problem also for an inductive circuit. So an AC circuit consisting of a pure resistance of 20 ohms and is connected across an AC supply of 230 volts 50 hertz. So find the current and power consumed. Sinusoidal equation for voltage and current. So here the given values are R is equals to 20, V is equals to 230, frequency is 50 hertz. We know that I is equals to V by R, so 230 by 20 which is equals to 11.5 amps. And P is equals to V into I, V is 230 and I is 11.5. So it is 2645 watts. So V maximum is equals to root into V, I maximum is equals to root into I. So root 2 into 230 which is equals to 325.27 volts and the current is root 2 into 11.5 that is equals to 16.26 amps. So omega is equals to 2 into pi into 5 that is 2 into pi into 50 which is equals to 314 and V is equals to V maximum sin omega t which is equals to 325.27 sine of 314 t volts and I maximum sin omega t which is equals to 11.5 sine 314 t volts. Okay, so this is how were we calculating the voltages and currents in a. This is also a pure resistive part, okay, resistive circuit, okay. So we have calculated the in a resistive circuit. Check. Now we will go for a pure capacitive circuit and it's a vector diagram. See, this is a pure capacitive circuit. uh, uh, an AC source is connected to a pure capacitor, and this is indicating the IC current which is flowing through the capacitor, and I is the current which is coming from the source. And here if you observe, the IC current is leading the voltage. Okay, so here the relationship between the current and voltages in a pure capacitive circuit. The relationship between the current through the capacitor and the rate of voltage change across the capacitor is as such. I is equals to C into dV by dt. So the expression dV by dt is the rate of change of instantaneous voltage over time in volts per second. So the capacitor C is in farads and the instantaneous current I is in amps. So capacitor opposes changes in a voltage by drawing or supplying current as they charge or discharge to the new voltage level. So the flow of electrons through a capacitor is directly proportional to the rate of change of voltages across the capacitor. So let me take an alternating voltage applied across the circuit is V, such that V is equals to V maximum sin omega t, and the charge on a capacitance at any instant Q is equals to C into V, which is equals to C into V is nothing but V maximum sin omega t. I is equals to dV by dt, okay, dQ by dt, which is equals to d by dt. Q is nothing but C into V, okay. So C into V is V maximum sin omega t. So which is equals to omega C into V maximum sin of omega t plus pi by 2. Okay, so derivation of sin omega t is this one. So here the value of I will be maximum, that is I maximum when sin omega t plus pi by 2 is equal to 1. So I maximum is equals to omega CV maximum, which is equals to V maximum divided by 1 by omega C. So from this is a part XC. So XC is equals to 1 by omega C. So here if you observe the current, first current start flowing. So it is leading the voltage. So this is a voltage V and this is a current I. The capacitive reactance XC, the ratio of the amplitude or magnitude of the voltage to the magnitude of the current in a capacitor. It is measured in farads and Xc is equal to 1 by omega C, and 1 by omega C is equals to 1 by 2 pi Fc. Okay. So the power consumed in the circuit is V into I, which is equals to V maximum sin omega t, I maximum sin omega t plus pi by 2. So V maximum, I maximum sin omega t into cos omega t. So V maximum, I maximum by 2 into 2 of sin omega t cos omega t. So which will give V maximum, I maximum by 2 sin 2 omega t. So the average power consumed in the circuit over a complete cycle, which is equals to T is equals to 1 by 2 pi, 0 to 2 pi. This is a complete cycle time period, okay? Minus V maximum, I maximum by 2 into 2 sin omega t into d of omega t, which is equals to 0. Okay, so this is a voltage and this is the current and this is the complete power. So the impedance is defined as a ratio of voltage to current. So impedance is V by I. This is an omega T, omega, okay. And this is a resistive part, and this is an inductor part, and this is a capacitor part, okay. This is a capacitor. X is equals to 1 omega T, XL is equals to omega L, and R is equals to constant, okay, which do not depend upon omega. So here the impedances of different components, that is R, capacitor, and inductor L, capacitor C, resistor R. So resistance VR into I is equals to R, and V and I are in phase. Capacitive reactance VC divided by I, which is equals to XC, which is also equal to 1 by omega C, and here V lags I by pi by 2. V lags I by pi by 2, or else I leads V by pi by 2, that is 90 degrees, okay. So inductive reactance, so here VL divided by I, which is equals to IL, which is equals to omega into L. Here V leads I by pi by 2, or else I lags by 90 degrees with V. So now we have discussed so many points. According to that points, we will solve one problem. So the problem is like that. A 60 microfarads capacitor is connected across 200 volts 50 hertz supply. Now determine a maximum instantaneous charge on the capacitor and the maximum instantaneous energy stored in the capacitor. So this is a given data, that is capacitor C is equals to 60 microfarads, so 60 into 10 to the power of minus 6 farads. Voltage V is equals to 200 volts, frequency F is equals to 50 hertz. So we know that the maximum value V maximum is equals to under root 2 into instantaneous RMS value. So here root 2 into RMS value is already given it as 200 volts. So root 2 into 200, which is equals to 282.84 volts, and the QM, which is equals to C into V maximum charge, so that is the maximum charge is equals to C into V maximum. C, we know that the 60 into 10 to the power of minus 6, and the maximum value of voltage is equals to 282.84, which is equals to 16.97 millicoulombs. That is a maximum charge. And maximum instantaneous energy stored, that is E maximum is equals to 1 by 2 into C into V square. So here 1 by 2 is zero point 0.5, C is 60 into 10 to the power of minus 6 into V2 is equals to 282.84 whole square. Have been asked maximum instantaneous value, so V maximum we are considering, so which is equals to 2.4 joules. So in this session, we have discussed about the differences between the resistance and inductive circuits and capacitive circuits. Yes, what was the differences? The resistive part will be in phase, and the reactive and the inductor will be 90 degrees, that the current will lag 90 degrees with voltage, and in capacitor the current will lead 90 degrees with voltage, okay. So we have understood the reactive capacitive reactance and the relationship for the current in capacitive currents, and the inductive reactance and the relationship between the voltages and currents in the inductive circuits, and the representation of the currents and voltage with vector diagrams, derivation of the relation between voltage and currents in pure resistive circuits as well as inductive circuits and as well as capacitive circuits, okay. So here capacitor voltage dash capacitor current by capacitor voltage, See, this is a capacitor. So a capacitor means always current will lead by 90 degrees. So voltage will lag by 90 degrees. Okay. So capacitor voltage lag capacitor current by 90 degrees. Okay. So which of the following statement is true? Instantaneous power is the sum of the voltages and currents? No. The instantaneous current is at the peak whenever the instantaneous voltage is at the maximum charge change. The instantaneous current is zero whenever the instantaneous voltage is at peak. It's B and C. Okay. For this is for uh, volt capacitor and inductor. Okay. In a pure inductive circuit, the instantaneous power is always it is positive and negative. We have observed in the waveforms. Okay. In an inductive circuit, current will always lag behind the voltage. Okay. In an inductive circuit, currents will lag behind the voltage. So these are the some of the important quiz points which you have to remember or understand. So if you understand, it will be obviously will be in your mind. Okay. So the average power in a single phase pure resistive circuit is always positive. Okay. The fluctuating part in an expression is P maximum, I maximum cos omega, cos 2 omega t. The phase differences in a pure resistive circuit is always zero. The average power in pure resistive circuit is P into I. So today we discussed about the resistor R, capacitor and inductor, reactance, inductive reactance, capacitive reactance, and we have checked the waveforms of the resistor, inductor, and the capacitor, and the vector diagrams of resistor, inductor, and capacitor. We have seen the differences between R, L, C, or R, XL, and XC, and we have gone through the voltage and current equations of these three components. So, from by today's session, I hope that you have got a clear idea about R, L, and C with their voltage and current representations. Okay. So, thank you so much for listening to my session. So, we will meet in the next coming session. Thank you so much.